Okay, this is Nathan Smith, Fresno Pacific University, continuing Chapter 5 for my managerial economics classes in North Fresno and Visalia. We were talking about regression analysis. Now we'll move to multiple regression analysis, which is much the same thing, but it's with more variables. So, okay, first of all, notice we had a model before. The model before was, it'd take me a while to find it, but the model before was just 1 was just an x, but now we have a whole series of them. For phi is just x, but now we have x1, x2, and so on all the way up to xk. We can have lots of different explanatory variables here. That means, by the way, you can't really visualize this as well. I mean, the way to think about it spatially would be as like an n-dimensional space, but of course that we can't visualize this. But the procedure is still intuitively as much the same as with single regression analysis. Okay, so suppose we have advertising, quality control, and sales. So we're interested in the correlation between these three variables. Without going into detail about the formulas, then you can calculate you can run a regression. What this shows you is the coefficients for each of the explanatory variables. So these say basically how much does the independent variable y, or sorry, the dependent variable y tend to change when these independent variables x1 and x2 change. So this tells you these linear estimates. If x1 rises by 1, y tends to rise by 1.87. x2, if it rises by 1, y tends to rise by 1.91. This is again the intercept, similar concept there. And then over here we get the t-statistics. These t-statistics are not as large as the ones we looked at earlier, but they're still significant. So, and now, how do you know they're significant? You have to know the critical value. The critical value, this is a rather small data set, so only 10 observations, so the critical value is higher than usual, but in a large data set, the critical value of t is about 1.96. And then the smaller the data set gets, then t starts rising a little bit, but I'm pretty sure these are significant at the 5% level. Okay, so then we have r squared. 93% of the variation is explained, which is more than what we had before, so we've explained more of the variation by including this other variable. And then a bunch of other stuff is calculated that we haven't gone into details yet. When I was running regressions for a living, then mostly I wouldn't even look at most of the things that it reported to me. Software packages report everything, why not? Computing power is super cheap, but you have to know how to pick and choose which indicators you're actually interested in. Okay, so we've got the coefficient of determination also applies at this level, and we tend to use a sort of a special formula to adjust it. Call it r bar squared, but it's basically n minus 1 divided by n minus k. What this does is kind of compensate for the fact that whenever you throw in another variable, you're always going to explain a little bit more of the variation. But that's a little bit misleading because the variable might really have no relationship. The new explanatory variable might be totally irrelevant, but you just get this misleading impression that it matters because, well, this compensates for that. So this basically says, yeah, if you throw it in an adjusted r squared, right? Maybe r squared rises, but if adjusted r squared doesn't rise, then that doesn't count. Something to bear in mind. In fact, here it reports both r squared and adjusted r squared. You see, so r squared is 93%, adjusted r squared is 91%. I can't remember what the r squared was before, but let's see. Come on, where's r squared? Previously 0.85. And now it's 0.93. So that's an increase, but it would always have to increase. Adjusted R-squared lets you say, okay, did it really increase? Yeah, actually it did in this case. It rose from 0.85 to 0.96. But in other cases, the adjusted R-squared might actually fall when you add another variable. So you can use adjusted R-squared for a single variable regression too. And if we wanted to add an x3 and x4 and try to explain even more of the variation, well, we'd use adjusted R-squared to check whether we're actually just throwing in irrelevant variables. Okay, so more statistics. Yeah, I guess you kind of want to know what all these mean to some extent. F equals unexplained equals explained variation divided by the number of degrees of the number of observations minus 1. K is the number of observations. I think I've got to tell you that so far. N is the total, or sorry, K is the number of regressors. N is the number of observations. So N minus K is called the number of degrees of freedom. And you notice that big problems happen if this N equals K. Is the unexplained variation gets divided by 0. Well, in general, it's not a good idea to run a regression in which N, the number of observations, is equal to K, or is less than K. You really can't find out anything in that case. You have to have, this makes sense, if you're, K is what you're trying to explain, and then N is the data that you have to explain it with, and if you're trying to explain a whole lot of things using just a tiny bit of data, that's not going to work. So yeah, the F statistic in this case, 46.6. And yeah, there's a set of critical values for this. I'm not going to go too much into how you use the F statistic for these purposes. To the extent we use this stuff, we'll mostly use the T statistic. But it's useful to sort of know these in the background. Anyway, regression analysis is full of pitfalls. So, full of pitfalls, by that I mean cases where it looks like you're explaining something and maybe you have picked up a genuine pattern, but you're misinterpreting it. For example, we've been talking about advertising and sales all this time. Well, what if sales are actually increasing just because consumer incomes are rising? And then advertising and quality control are increasing. Maybe quality control is increasing because quality control is kind of proportionate to the amount that you're selling. So whenever you increase quality control, then you have to, or whenever you increase sales, you have to raise quality control. And maybe the same is true with advertising, where the advertisers just kind of automatically get a certain share of the budget. So it could be that there's a totally different causal chain going on. We've been assuming that advertising promotes sales, but maybe that's not the story. Maybe something totally different is going on. That would be an example of multicollinearity. You've got different explanatory variables that tend to result in multicollinearity. Two or more explanatory variables are highly correlated with the other. You don't really know which one is explaining the variation. So that's something to look out for. Heteroskedasticity. So this would be the methods that we've used so far tend to assume that that the error term is the same regardless of what the y variable is. If you want to correct for heteroskedasticity, you have to use somewhat of a slightly different regression methodology, so that's something to look out for as well. Autocorrelation. This occurs if the error terms are correlated with each other over time. Another way to think of this is that time is sort of acting as an omitted variable. And so it's important to understand these, because a lot of times if you don't understand these, then you can report regression results that are quite naive and where there's something going on that's kind of not very substantive that's really driving the result. So these are the game statistical analysts have to play, always trying to control and deal with these things. This shows heteroscedastic disturbances here. So in this case, there's a lot more variation here, up here at the upper end of the, when the dependent variable is high than when the dependent variable is low. This is the opposite. Got a lot more variation when the dependent variable is low. Autocorrelation. You see here, if you were just going to run a regression, well, there's obviously something going on here where the previous turn, much of the impact carries over to the next turn. This is negative autocorrelation. So here, if the variable was high last time, it tends to be low, and vice versa. And all of these would create problems for your regression results. The Durbin-Watson statistic, this allows you to test for autocorrelation, and if you think about how the statistic was constructed, I'm not sure what all the deep reasons are for picking this particular statistic, but you may be able to see why this is a test for autocorrelation. Because what you do is, down here we have a summation over all the observations. Here we have a summation over all except the first one. And you notice what we're doing? Compare the error term in period t to the error term in period t minus 1, subtract, and then we take this this value squared. So, okay, so why is autocorrelation absent if d equals 2? These error terms, if they're not autocorrelated, then often one will be positive and the other will be negative. So then you actually get the error term is larger, and so then when you square this, then that error term sort of gains a lot of extra weight. And if you have quite a bit of that, you end up with d equals 2. If you got something that's much lower, then you'd have something that's that would be autocorrelated. That would be an indication that you had an autocorrelated time series. And what you have to do then is you sort of have to control for the time trend. And you have to take that into account directly, because you have to control for the time trend. You have to control for previous periods. So there's methods to compensate for that. Don't worry too much for now about what they are, but that's just something to be wary of. Okay, so if you want to estimate demand, what are the steps? So first of all, model specification. This is where you have to have a theory about what's determining demand. And it has to be kind of plausible, and it has to be somewhat comprehensive. You don't want to leave anything out. If there's something that's going to be really important, then you don't want to leave that out of your regression. Then you go out and collect data. So you find out what the values of the relevant variables were. Then you have to define a functional form. So this is a little bit tricky, but depending on the variable, it might vary with the square, it might vary with the log. There might be various possible relationships between those two. Maybe it's the log of one depends on the log of the other. And then you do hypothesis testing to see if you've really come up with significant results. So, okay, so we can assume here a linear function. Is this a demand function? Yeah. Qx is the quantity demanded of good x. We've got the price. We've got income. We've got n is the number of consumers. We've got the price of some other good, y, that might be relevant to x. Maybe it's a complement. Maybe it's a substitute. Then you have some error term at the end. So this is your model you're assuming. In this case, we're assuming a linear function. But you could have other functional forms. Maybe there's a power function. Maybe it's the product of the two. That would, I mean, if it's consumer incomes and the number of consumers, it makes sense that maybe what matters there is really the product of these two. And it could be a log relationship as well. This would look a little bit different. And sometimes by looking at the data, you can kind of get an idea of what kind of functional form is relevant. You can kind of eyeball if you know something about the functional forms to begin with. Or you might, based on theory, you might have a reason to believe that the relationship between two variables has a particular functional form. So, this is an example of, this is basically just some data that exports and imports in 2009, major U.S. exports. We export agricultural products, chemical, automobiles, civilian aircraft. Major imports, petroleum products, apparel, automobiles, household appliances. Top trade partners. I'm not sure exactly. I don't remember exactly why they include this. Yeah. Well, that's it for chapter 5. That's probably enough material.